Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to our 32 lecture of MTH108 Business Math 1. Today we will continue with our chapter 14, which is about probability distributions. What we have studied so far in this chapter, we have studied the definition of random variable and the types of random variables as discrete random variable and continuous random variable. The frequency distribution and the relative frequency can be obtained by knowing the frequency distribution of that particular value of the random variable. And relative frequency is nothing but the probability distribution. Some properties of the probability distribution which are same as the properties of the probability function. And with the help of the histogram, how we can describe our random variable and the respective probability distribution. Then we have seen some measures of central tendency, that is the mean, median and mode, and the formula for mean of discrete probability distribution. Then we have studied the extremes of variations, that is, we are interested in knowing that what attributes can further define our data set other than the mean, median and mode. For this we have calculated or seen the extremes value of our data set and calculated the range. But we have found out that the information about the range is not enough to the variation of our data set. So we have defined the average deviations from the mean by knowing the deviations from the mean, and we have seen that these average deviations are actually 0. So further continuing in this direction, we have taken the squares of the average deviation, adding all of them and dividing by the total number. We defined the variance of our data set, but the variance does not give us the accurate information about the variation of our data set. So for this, by taking the square root of our variance, we have defined the standard deviation, which is most commonly used to define the variation or the spread of our data set. That is how far the points are from the mean and how close they are from the mean. And the formula for the standard deviation of the discrete probability distribution, that is the case when we are given with the data set and the probability distribution. Then we have studied some type of probability distribution, that is the binomial probability distribution. But for this type, first we have studied the Bernoulli process, that what types of process or experiments come under this category and what are the characteristics of a Bernoulli process. Using this information, we have defined our binomial probability distribution. Some examples to see clearly what is the binomial probability distribution in that case, and some calculation in the form of a graph, that is by using the histogram. Then we have seen some two basic formulas, that is about the mean of a binomial probability distribution and the standard deviation of a binomial probability distribution. And these two formulas can easily be calculated by knowing the number of trials, n, the probability of success, p, and the probability of failure, q. Today we will discuss one more important type of probability distribution, which is known as the normal probability distribution. Now, up to now, or in our last lecture, we have constantly emphasized on the discrete random variable and discrete random variable. So up to now we have discussed the discrete random variables and the probability distributions with respect to them. That is the binomial probability distribution, where the random variable is discrete and the process is a Bernoulli process, which means that the other type of random variable, for example, if we have a continuous random variable, then this binomial probability distribution is not sufficient or not applicable for that type of random variable. So if, for example, we have a case of continuous random variable, then what will be the perfect probability distribution satisfying that particular case? We have seen one example of continuous random variable in our previous lecture of this chapter, and We have seen that there are many experiments which deal with the continuous process. For example, the example which we have discussed in our previous lecture of this chapter was a student is taking an exam with a 1 hour time limit. That is, our random variable x will have the possible outcomes small x, where small x belongs to the half open interval 0 to 60. Or our capital X, 0 is less than x is less than equals to 60, or in other words, our random variable strictly lies between strictly greater than 0 and less than equals to 60 minutes. So this is an example of a continuous random variable. And if a random variable can assume any of the infinitely many values within some interval of real numbers, it is called a continuous random variable. This is the same definition which we have defined in our previous lecture of this chapter. Some examples of continuous random variable may be the scores in the NTS exam, about the height of the people, about the length of the leaf. These are all continuous process, and they come under the category of continuous random variable. Similarly, we can define continuous probability distribution, that is a complete listing of all possible values of a continuous random variable x along with all the probabilities of each value. So the number of possible values for the random variable is clearly infinite. And for these type of distributions, the probabilities are assigned only to intervals of values for the random variable. So there is a difference between the continuous probability distribution and a discrete probability distribution. In the case of discrete probability distribution, we assign the probabilities to the particular outcomes of our random variable. But in this case, the probabilities are assigned only to the intervals of values for the random variable. For example, the annual rainfall in an area, if we measure it in inches, is a continuous process, and the number of possible amount of rain is infinite. That is, the random variable has actually infinite possible values. That is, the random variable in this case has values x is equals to small x, where x is greater than equals to 0, or x belongs to the interval 0 to infinity. So the number of random variables or the possible outcomes are infinite, which means that in the case of distributions, we cannot assign the probability to each particular outcome. In fact, we have to group them, and we have to assign the probabilities only to the intervals containing that particular outcome in which we are interested in. For example, one possible outcome can be that is the amount of rain is 24 inches in that particular area. Then the infinite possible values, they may be extremely small or extremely large. For example, the infinite possible values may lying between, for example, starting from 0 to 0.1. These are possible outcomes of our continuous random variable. They can be very small and they can be very large. So with this type of distribution, we are not concerned about the probability that a random variable will assume at a specific value, because for one reason the possible values of a random variable are infinite. We cannot assign the probability to each possible outcome. They can be very small, can be very large. So we are interested in the probability that a random variable will assume within a defined interval. For example, in the case of rainfall, we say that one particular possible value of our random variable can be equals to 24 inches, then we may be concerned in knowing the probability that annual rainfall will be between 24 and 25 inches. So we will define an interval which will contain that specific outcome of our random variable, and we will assign the probability to that particular interval. That is, the probability will assign in this case to the annual rainfall for the interval between 24 and 25 inches. And now we define our normal probability distribution. Okay. So this type of probability distribution deals with the continuous process, because in our last lecture when we were discussing our binomial probability distribution, we were emphasizing all the time that the random variable should be a discrete random variable with the Bernoulli process. So whenever we have a continuous random variable, the probability distribution that will deal with that process or experiment or trial will be the normal probability distribution. For example, the scores of students in NTS exam, about the height of the people, about the length of the leave, and so on. And in this case, for measurements as opposed to counts, the graphical representation of the distribution of a continuous random variable can look like, this is our random variable x and the relative frequency, then this may look like this. Because we are not referring probabilities to some particular counts, so the graphical representation of the distribution of a continuous random variable x will be like this, where this is our value mu. That is, we have a bell-shaped or a normal curve. So this will be the graphical representation of our distribution of a continuous random variable. That is, in particular, this will be the graphical representation of a normal probability distribution. And now we look at the graphs. Okay, first we have this is our x-axis and the relative frequency. Suppose we have one graph as this and the second graph as this. Then in this case, if we look carefully, and here we have one middle line mu, and this middle line is nothing but our mean of our data set points. So if we look at both of the graphs, see that both the graphs have the same mean, but they have different standard deviations. That is, both of the graphs have the normal distribution, and the mean is the same for both of them, but the standard deviation sigma is different. That is, what do we mean by the standard deviation? The standard deviation basically tells us the distance of the point from the mean. That is, how far the points are from the mean or how close they are from the mean. So if we have our normal distribution, which is a bit narrow, which means that the standard deviation is small and the points are close to the mean. If we have our normal distribution a bit wide, which means that the points are a bit far from the mean and the standard deviation is large. That is, in this case, in the first case, if this is the standard deviation, and in the second case, this can be the standard deviation. So the type of curve tells us about the standard deviation or about the distance of the points from the mean. We may consider two more graphs again. For example, we have one graph as this and one more graph as this. Then both the graphs have same standard deviation, but they have different means. That is, the first graph has mean mu1, the second one has mean mu2, but they have the same standard deviation. That is, in both the data points they are at the equal distance from the mean. That is, here we have standard deviation as same, but mean they are different in both the cases. So by looking at the graph is symmetric about the mean, this mu, and the narrowness or the wideness of the graph tells us about the standard deviation being small or large. That is, if the graph is narrow, standard deviation will be small and the points are close to the mean, and vice versa. So there may be many normal distributions with same mean but different standard deviations, with same standard deviations but different mean, and so on. And now we summarize some properties of the graph of a normal probability distribution. The normal curve is symmetrical about an imaginary vertical line which passes through the mean. That is, in both the cases, these graphs are symmetric about an imaginary vertical line, and that vertical line passes through the mean of our data set. That is, the graph on the right side of this vertical line, it will be exactly same as on the right side, as on the left side of a vertical line. For the sake of simplicity, we draw a graph here again. Okay. And the symmetry means the height of the curve is the same if one moves equal distances to the left and to the right of the mean. That is, if this is our mean, then this height of the curve is the same if either we move on the right side of the mean or on the left side of the mean. The tails of the curve come closer and closer to the horizontal axis. That is, these tails, they come closer and closer to the horizontal axis, and they never cross the x-axis, no matter how far one moves to the left or to the right of the mean. And the areas under the curve represents the probability distribution and are equivalent to the probabilities actually. That is, area under this curve represents the probability distribution are equivalent to the probabilities. And now we come to the graphs and the probabilities. That is how we can find the probabilities from the graph of a normal probability distribution. Now, if the total area under the normal curve is equals to 1, the probability that a random variable will assume a value between a and b equals the area beneath the curve and bounded on the left and the right by the vertical lines x is equals to a and x is equals to b. That is, what do we mean by this? This is our normal probability distribution. And if the total area under this normal curve equals to 1, that is why this is equals to 1? Because we have just said that the areas under the curve representing the probability distributions are equivalent to the probabilities, and sum of all the probabilities is equals to 1. So the area under this normal curve is equals to 1. If we are interested in knowing the probability that a random variable will assume between two values a and b, let's say this is the value a and this is the value b. That is the value when the random variable has x a and when random variable has value b. So We are interested in knowing the probability that a random variable will assume in some interval, not at specific particular point, and between A and B. Then this is equals to the area beneath the curve, that is the area beneath this curve, and bounded on the left by the vertical line x is equals to A, on the right by the vertical line x is equals to B. So this will be the area under this curve, which is actually the probability of the random variable between the values A and B. So this is how we define the probability from the graph of a normal probability distribution. That is, here the probabilities are not assigned to some specific values, but they are assigned to some particular interval containing that specific value. And the probability of the random variable assuming between two values will be the area under that curve surrounded by the two vertical lines. And now we define the areas under the normal curve. The standard deviation plays a significant role in describing probabilities associated with a normal random variable x. Or more precisely, the probability that x will lie within one standard deviation of the mean is approximately 0.68. What do we mean by this? That approximately 68% of the area under a normal curve is within one standard deviation of the mean. So let's draw our curve of standard deviation again. If this is our curve of a normal curve and this is our mean mu, then we are saying that the probability that x will lie within one standard deviation of the mean is approximately 0.68. If this is our standard deviation sigma, so this point is equals to mu plus sigma and this point is equals to mu minus sigma. So the probability that our random variable will lie within one standard deviation, that is in this region of the mean, that is this region we are talking about, is approximately equals to 68%. And how do we write it? We write it as the probability of mean minus sigma less than the random variable less than the mean plus the standard deviation is equals to 68%. These are very well known facts about the area under the normal curve. That is, the area under the normal curve with one standard deviation is 68%, and we continue that the area, this is our x and f of x, and we have our, this should be like this, okay. This is our normal curve, this is our mean mu. Let's say this is our standard deviation, one standard deviation mu plus sigma, and on the negative side we have mu minus sigma, which means that this length basically is equals to sigma. Let's say we have this length as again equals to sigma, so by adding it to the mean we obtain mu plus 2 sigma, continuing mu plus 3 sigma, and the same process on the left side of our mean, mu minus 2 sigma, mu minus 3 sigma. For example, we consider this as our curve, then we know that the area under a normal curve with one standard deviation is equals to 68%. The area under the normal curve with two standard deviations, that is this part, is also included on both sides. This we say is approximately equals to 95%, that is this part, including this part, and the distance and the area under the curve with 3 standard deviations, that is this part including all this part, is equals to 99.7%. And how we will write them? That is the area or the probability of our random variable x with 1 standard deviation is 68%, with 2 standard deviation, with 2 minus sigma is less than mu plus 2 sigma is equals to 95%, and the probability with 3 standard deviations is equals to 99.7%. So these are some well-known facts which we know about the area under a normal curve, or the probability of a random variable with 1 standard deviation, with 2 standard deviations, and with 3 standard deviations. And now, using this information, we come to some examples. First, we are asked to find the percentage of the people that take the SAT exam and make the score between 330 and 530. What is the percentage of the people which score between 330 and 530? So first we have to find the mean. We are provided with 2 numbers, so the mean will simply the average of the 2 of them, that is adding the both dividing by 2, and the mean is equals to 430. Okay, what else we need? We need our standard deviation sigma, which is equals to 330 minus 430 square plus 530 minus 430 square divided by 2 and whole to the power 1 by 2, which is equals to 10,000 100 square plus again 100 square divided by 2 under root, which is equals to 100. So this is our mean mu and this is our sigma 100. Okay. Now what is 330 actually? 330 is equal to mu minus sigma, and 530 is equals to mu plus sigma. What we have to do? First we have to find the mean, then the standard deviation, then we have to write our given data points in terms of mean and standard deviation. Okay, that is in terms of 1 standard deviation or 2 standard deviation. Now here 330 is 1 standard deviation to the left of mean, and 530 is 1 standard deviation to the right of mean. So our graph will be, this is x and this is f of x. This is our mean mu, which is equals to 430. Now standard deviation is equals to 100, which means that 100 units towards the right from mean. If this is equals to 100, so this will be equals to mu plus sigma, which is equals to 530. If this is 100 units to the left of mean, so this will be mu minus sigma, which is 330. And we are asked to find the percentage of the people who will score between 330 and 530, which means that we have to find the area under the curve, under this curve, with the 2 vertical lines bounded by mu minus sigma and mu plus sigma. That is, we have to find the area under this normal curve with 1 standard deviation. So the percentage in this case will be equals to, or the percentage of people that score between 330 and 530 is 68%, because these two values lie on one standard deviation from the mean. So the total area of this under this normal distribution is 68%, and that is our answer. Let's have a look at one more example, that is what percentage of people that take the SAT exam make scores between 420 and 780. And now we have different mean and the different standard deviation, where this small sd stands for the abbreviation of the standard deviation. Okay, so our mean is 600, sigma is 90, which is given now. Okay, and what will be the value of this 420? 420, first we have to check what is 2 sigma. 2 sigma is 180, and mu minus 2 sigma is 600 minus 180 is 420. Now we look at the other extreme. Mu plus 2 sigma is equals to 780. So these are the extremes with two standard deviations. That is, if this is our normal curve with the mean mu as 600 with one standard deviation as 690, the second with on the left side is 510. Okay, and the second standard deviation as 780, and on the left side we have 420. So we are asked to find the percentage of the people that will score between 420 and 780, and this is equals to mu plus 2 sigma, mu minus 2 sigma, that is 2 standard deviation and on both sides. So in this case we know that the area under the normal curve, or the probability of the random variable for 2 standard deviations, that is mu minus 2 sigma is less than x is less than mu plus 2 sigma is equals to, writing them in the form of the values, particular values, that is x lies between 420 and 780 is equals to 95%. Similarly, if we are asked to find the probability for 3 standard deviations, then it will be 99.7%. We will simply calculate that mu plus 3 sigma and mu minus 3 sigma, and the probability or the area of the under the normal curve for those particular values will be 99.7%. That is the area near this, including, that is the area including this and this. Now let's have a look at one more example. We are asked to find the percentage of the people that take an exam and make scores between 70 and 85 with mean 70 and standard deviation as 7.5. Okay, first we draw the graph of our standard deviation, or the graph of our normal distribution. Now this is the graph of our normal distribution with mean mu is equals to 70. Now the standard deviation is 7.5. So our first point 70 is equals to mu, that is the first point lies on this mu. Now mu plus sigma is 77.5 and mu plus 2 sigma is equals to 85. So our second point is mu plus 2 sigma, that is this is our sigma point mu plus sigma, and this is our 85, which is mu plus 2 sigma. And we have to find the percentage of the people whose scores lie between 70 and 85, that is between these values. In our previous two examples, if we observe that we have found the area under the normal curve or the probability of our random variable for the symmetric portion about the mean. That is, in our previous example, in this example, we were asked to find the percentage scoring between 420 and 780, and this was symmetric about the mean with 2 standard deviations. Similarly, in our first example, we were asked to find the percentage of the people scoring between 330 and 530. By looking at the graph, this was also again symmetric to the mean with 1 standard deviation, that is 1 standard deviation to the right of mean and 1 standard deviation to the left of mean. And by knowing the area under the normal curve, some standard area under the normal curve, we have found the percentage with 1 standard deviation and with 2 standard deviation, that is 2 standard deviation to the right of mean and 2 to the left of mean. But in this example, we are asked to find the percentage or the probability of the random variable lying between 70 and 85. That is, we have to find the probability of 2 standard deviation, but only to the right of it. The left part is not included or not required to answer. One way to do is, since we know that 85 is mu plus 2 sigma, that is 2 standard deviation, so by taking the 2 standard deviation to the left of mean, we have our probability as, we have our value score as 55, and the probability in this case minus 2 sigma less than mu plus 2 sigma is equals to, okay, which is equals to 95%, which is equals to 0.95. And we are only interested on the right side of our mean, that is 2 standard deviation from the right of mean. We can divide it by 2, that is the probability of x between 70 and 85 will be 0.95 divided by 2 will be equals to 0.44, approximately equals to 0.447, will be approximately equals to 0.477. Now one way to find it in this way, but this cannot be done in every time, because in this case we were lucky that we have the information about the area under the 2 standard deviation from the mean, and we were asked to find only the right side of the 2 standard deviation from the mean. So by calculating the area or the probability and dividing it by 2, we obtain only on the one side. But in order to determine this kind of probability in general, we take the advantage of a very useful property of our normal distributions, which says that any normal probability distribution with mean mu and the standard deviation sigma can be transformed into an equivalent standard normal distribution which has a mean equal to 0 and standard deviation equal to 1. And the transformation redefines each value of the random variable x in terms of its distance from the mean, stated as a multiple of the standard deviation. What do we mean by this? So far, in our first two examples of finding the percentage of the scores lying between some particular range, we have defined, this is our probability distribution with mean mu. What we have done so far, we have defined sigma, that is mu plus sigma, mu plus 2 sigma plus 3 sigma, and same thing on the left hand side. And so on. So what do we mean by transforming that into an equivalent standard normal distribution which has mean equal to 0 and standard deviation equal to 1? That is, this mean will be equals to 0 and standard deviation is equals to 1, which means that the transformation redefines each value of the random variable x in terms of its distance from the mean, stated as a multiple of the standard deviation. That is, since this distance sigma is equals to 1, so we obtain mu plus sigma, similarly mu plus 2 sigma, as in terms of our in the multiples of our standard deviation. Or we obtain this as 1, since mean is 0, sigma is 1, this as 2, this as 3, and on the left side with the negative values minus 1, minus 2, minus 3, and so on. So we have transformed our normal distribution into the standard normal distribution by redefining our scale on the x-axis as mean equals to 0, standard deviation sigma equals to 1, and then the mean value will be equals to 0, the value mu plus sigma will be equals to 1, mu plus 2 sigma equals to 2, and same on the left side, that is mu minus sigma equals to minus 1 equals to minus 2, and so on. So this is how we have transformed our normal distribution into our normal curve into the standard normal curve. That is, the normal curve is such that 50% area is to the left of our mean and 50% is to the right of our mean. The area between mu plus sigma and mu minus sigma is actually the same. That is, the area between this region is same as the area between this region. That is, we have transformed our random variable. That is, we have transformed our random variable to the number of deviations from the mean. That is 1 unit from mean, 2 units from mean, and so on. And now we define the formula about this transformation known as the Z transformations. We have transformed the original distribution into the standard normal distribution by equating Z values for the pertinent X values as our Z variable is obtained by the particular value of our random variable in which we are interested in minus the mean divided by the standard deviation. And its values are the units of standard deviations. That is, the values of our Z are the units of standard deviation from the mean, which are usually called as the standard units. And the Z value corresponding to the mean is always equals to 0. That is, when our X is equals to mean, then the corresponding Z value will be equals to 0. Now we come back to our example in which we were interested in finding the percentage of the people that have scored between 70 and 85 with mean equals to 70 and standard deviation equals to 7.5. We have seen one way of finding the percentage because the number 85 was 2 deviations right from the mean. We have calculated the area, total area of 2 deviations from the left and to the right and divided by 2. But we will see in our later examples that this type of application or this procedure is not applicable in general. So we have to transform our data into the standard normal curve. So the z value, or transform it into the z transformations. So the z value corresponding to a score of x equals to 70 will be equals to 0. Why? Because we have just seen that the z value corresponding to the mean is always equal to 0. Now the z value corresponding to a score of x equals to 85 will be equals to the required value minus the mean, which is 70, divided by the standard deviation. So the z value is equals to 2. Okay, now this is our x, this is our graph. The mean mu is equals to 0 now. Now the 1 units and the 2 units. Now if we have the z value equals to minus 2, which means that we are on the left side of our mean. So the sign indicates that we have to calculate to the right side of the mean or to the left side of the mean. So the z value is equals to 2. This we have also seen in the previous calculations of this example, that 85 was 2 standard units to the right of the mean, and we have to find the area of this lined region. Okay, now we know the z value. For this we need the table which is given in the book on page 646. The z value for equals to 2 given in the table as the first column, and the row when it appears 2.0, and this is equals to 0.4772. So the probability of our random variable x scoring between 70 and 85, and writing this probability in terms of z variable, that is, this will be equals to our z variable between 0 and 2, that is, this is the value when z is equals to 0, and this is the point when z is equals to 2. So this is equals to, from the table, is equals to 0.4772. Now if we are also interested in finding the probability, that is the percentage of people scoring between 0 and 85, that is the percentage of people scoring between 0 and 85, that is the probability of our, in terms of z transformation, will be equals to of our z less than equals to 0. Since we can see that z is equals to 0 is this point, so 2 units from the right will be equals to z equals to 2, and now we are interested in finding the area or the probability or the percentage of the people scoring between 0 and 85, that is all this included in our previous graph. That is people who have scored 0, who have up to 85. So in this case we have to divide our probability in 2 parts. First part on the left side of our mean, and the second on the right side of our mean. On the left side we say that whenever z is negative, that is less than 0 from this mean to the left side of the curve, plus whenever z is between 0 and 2. Okay, since in the properties, if we go back to the properties, We have said that the normal curve is such that 50% area is to the left and 50% to the right, which means that 50% area is to the left of our mean, which is equals to, in terms of probability, will be equals to 1 by 2. That is, it will be equals to 0.5, because the area under this curve, this normal curve, is equals to 1. That is, the sum of all the probabilities is equals to 1. So the probability of the area to the left of the mean is 1 by 2, and the probability between 0 and 2, which we have already calculated, which is equals to 0.972. That is, 97.2% people, 97.2% people have scored between 0 and 85. So by transforming our x-axis to the z transformation by calculating the corresponding z value, we can easily obtain the area under the required region. If we look at our second case, that is the probability between 0 and 85 cannot be found by adding all the properties and subtracting this percent. In this case, we have to transform to standard normal curve, and then we will find the corresponding property. One more example. A survey of per capita income indicated that the annual income for people in one state is normally distributed with a mean of $9,800 and a standard deviation of $1,600. If a person is selected at random, what is the probability that a person's annual income is greater than 5,000, greater than 12,200, between 8,520 and 12,200, and between 11,400 and 13,000? First, we will find the probability of a person's annual income greater than 5,000. That is our part A. We are interested in finding the probability of x greater than 5,000. The first step which we have to do, we are provided with the mean as 9,800 and standard deviation as 1,600. So the first thing which we have to do is to find the corresponding z value of this required number. So the z value will be equals to 5,000 minus the mean divided by the standard deviation, which is equals to minus 4,800 divided by 1,600 is minus 3. Okay, minus 3 clearly tells us that this is our mu equals to 0. Minus 3 clearly tells us that we have to work on the left side of our mean. That is, this is our value minus 1, minus 2 and minus 3. So we have to find the probability when our z is greater than minus 3. That is, the percentage when a person's annual income salary is greater than 5,000. That is, we have to find the area under all this region. So how we will proceed? That is, we have to find the value of this corresponding z value when z is greater than equals to strictly greater than minus 3. Again, we have to split this value in two parts, that is on the left hand side and on the right hand side. On the left hand side, we say that when z lies between minus 3 and 0, plus when on the right hand side when z is greater than equals to 0. So on the left hand side symmetric curve, 50% area lies on the right hand side, so this will be equals to 0.5 straight away. That is, the area under this curve is 50%. And for the probability between minus 3 and 0, we have to check the value of z is equals to 3 from the table, that is from the first column, and the point where we have z is equals to 3. In this case, the probability is given as 0.49865, and adding these two, we will obtain 0.99865. That is 99.865% people have annual income salary greater than 5,000. Have annual income greater than 5,000. The second part was greater than 12,200. Okay, that is probability of x greater than $12,200. So the corresponding z value will be equals to 12,200 minus the mean divided by the standard deviation, which is equals to 2,400 divided by 1,600 is 1.5, which means that if this is our mean, mu equals to 0, and this is our 1 unit right to the standard deviation, and this is 2 units right to the standard deviation, we are interested in finding the area between this line mean, and this. So this is the area between 0 and 1.5, and we have to find the probability of this green lined region, not the red lined region. In this case, we know the corresponding z value, that is, we have to find the probability of x greater than 12,200, which is equals to the probability of z greater than 1.5. Since we have to find the value of z greater than 1.5, so we will break it in two parts, that is the probability of z greater than 0 minus the probability of z between 0 and 1.5. We know the probability of z greater than 0 is the area to the left of the mean having the probability of 0.5, and the probability between 0 and 1.5 can be seen from the table as 0.4332. Subtracting this, we obtain it is 0.0668. So this is the required probability which we have to find. If we will simply calculate the value from the table for z equals to 1.5, we will get this number 0.4332, which is not the exact number reflecting which we are interested in. So we have to subtract the probability between 0 and 1.5 to the total probability when z is positive, and then we will obtain our required region. The third point which we have to find is the probability between 8,520 and 12,200. Okay, we know the z value of 12,200, which is equals to 1.5. The z value of 8,520 will be equals to 8,520 minus the mean divided by the standard deviation, which is equals to minus 1280 divided by 1,600, which is equals to minus 0.8. So if this is our curve, this is mu equals to 0, and this is our 1.5, and this is minus 0.8. So we have to find the probability of the area under the standard normal curve between minus 0.8 and less than 1.5. That is the probability of 8,520 of the random variable between the interval 8520 and will be equals to the probability of z between minus 0.8 and 0 plus the probability, that is the z between 0 and 1.5, that is between minus 0.8 and 0, this portion, plus between 0 and 1.5 is this portion. So from the table we can see that the probability when z is 0.8 is 0.2881, plus for the case of 1.5 is 0.4332, which is equals to 0.7213. And now the case, that is the probability between 11,400 and 13,000. So the z value for 13,000 will be equals to 13,000 minus the mean divided by the standard deviation is equals to 2. The z value for 11,400 is this value minus the mean divided by the standard deviation is equals to 1, which means that we have to find the area between 1 and 2, that is only this region. So the probability in terms of z will be equals to 1 is less than z is less than 2. So the value of z from the table when it is, so this can be written as the probability or the value of z when z is between 0 and 2 minus the probability when z is between 0 and 1. And for the case of z is equals to 2, from the table it is 0.4772 minus for the case of 1 is 0.3413 and the probability is 0.1359. How we have calculated this specific region which is not symmetric about the mean? The total probability from 0 to 2 minus the probability from 0 to 1 will give us the required probability. Now few more parts which appear as the practice exercise of the same question, that is the probability when the annual income is greater than 8,200. So the z value will be equals to this value minus the mean divided by the standard deviation, which is equals to minus 1. Okay, this is our mean and the z value for minus 1, that is this region we are interested in. Okay, minus 1, that is this region, and the x is strictly greater than this value 8,200, which means that this region is also included. So our lower limit in this case is minus 1 and we do not have any upper limit. So the probability in terms of z will be equals to when z is greater than minus 1, that is splitting it in terms of origin, we obtain when z lies between minus 1 and 0 plus when z is greater than equals to 0. So the value of z when x is equals to 1 is 0.3413. The value of z is equals to 1 is same as the value of z is equals to minus 1. That is, the value of z is equals to 1 is same as the value of z is equals to minus 1. So from the table we will simply look at the value of z is equals to 1 plus 0.5, that is the area under on the right hand side of the mean is 50%, adding them 0.8413, that is 84.13%. 84.13% people will have the annual income greater than 8,200. And the last part of this example, that is the probability when a person's annual income lies between 9,000 and 13,000. So the z value for 13,000 we already know is 2. The z value for 9,000 will be equals to this minus the mean divided by the standard deviation, which is minus 0.5, which is minus 1 by 2. That is, we have to find the values between minus 0.5 and 2, that is this region. So the value of minus z between minus 0.5 and 2 will be splitted as the value of z greater than equals to minus 0.5 plus the value of z between 0 and 2. And from the table we will see that the value of z is equals to 0.5 is 0.1915 plus between 0 and 2 is 0.4772, which is equals to 0.6687. That is 66.87 people have annual income between 9,000 and 13,000. So we end up with the examples of finding the normal probability distribution, and we have one important observation, that the probability of occurrence of any specific value of the variable equals 0. That is, for any point A, the probability that the random variable has that specific value is equals to 0. And we have concluded that for any two constants A and B, with A less than B, the probability that x is greater than equals to A and less than equals to B is same as the probability that x is greater than A and less than equals to B is same as the probability that x is greater than A and less than B is same as the probability that x is greater than equals to A and less than B. That is for all types of intervals, 4 intervals: closed interval, the open interval, and the semi-open intervals. The probability is the same. So what we have concluded, that our table, which gives the values for some same value for the positive z and same for the negative z, so we conclude that our table represents the probabilities that our z transformation z will assume the values between two endpoints z1 and z2. Where the exact value of z1 and z2 may not be included. That is, where the exact value may not be included. But in all the cases, either the end values are included or not, the probability will be the same. May not be included, as in the case of part A of our previous example. That is, the person's annual income greater than $5,000 or greater than equal to $5,000. In both the cases, it was the same, because we have looked for the corresponding Z value in the table, and no matter the endpoint is included or not, we will obtain the same answer. So this is how we calculate the normal probability distributions, provided if our points are not symmetric about our mean and the standard deviation. We will transform it into the standard normal curve, find the corresponding Z value with the help of the formula, and then we will find the respective percentage or the area under our normal curve. With this, students, we end our today's lecture, and we also end our course about the Business Math 1. We have some practice questions from the section 14.4, and let us summarize what we have studied today. We have studied today the continuous random variables and the continuous probability distributions with some examples. And then we have seen that the normal probability distributions deals with the continuous random variable. And what do we mean by the graphs of normal distribution, and some properties which the graph of our normal distribution tells us. The probabilities which we can obtain from the graphs, and the area under the normal curve with some examples. Then we have obtained the standard normal curves, and by using the Z transformations we can find the probability under any specific interval or specific region of our curve, and we have seen some examples. With this, we end our course, and in case of any difficulty you may contact me at my email address or contact the respective tutor. With this, Allah Hafiz, students, and hope you have enjoyed this course. Allah Hafiz.